All right. Welcome back. And then today we'll have the last piece, which will be on how to handle image, video data. And so we're going to have the last tutorial on vision transformers. So we'll have Bharath Ramsundar, who's going to give the tutorial, and then Amal, who's going to run through the code walkthrough, and the file it's on GitHub, so you can follow along there as well for the tutorial. Okay, all right. With that, I'll hand it over to Bharat. Thanks for doing this.
All right, pleasure. So I can't see anyone in the audience, so if anyone has questions, I guess raise them on the chat, and then we'll try to kind of jump in. For this,
Yeah. So yeah, the questions in the room, I will coordinate with you, and I'll interrupt, and you'll be able to hear it. I'll give the mic to them and ask the question. Thanks.
Okay, excellent. Thank you, Venkat. All right, so I think with that, let's jump maybe right into the tutorial for vision transformers. So I believe you all have seen some use cases of transformers already in the tutorials here. And the goal of this tutorial, I think, is to talk about how transformers first are making a dent in vision applications, but probably more relevantly, talk about how transformers can be useful for scientific applications. Just to sketch it out even before we dive into it, at the end of the day, if you look at like any PDE system, you're dealing in many cases with the 2D or 3D PDE where you have a type of image. If you have an image, you can feed that into a vision transformer, which gives you a lot of ability to kind of reharness the infrastructure that's been built for transformers elsewhere. To maybe answer another quick question, you could very reasonably ask, why can't you just use a convet? And the answer is you probably could, but there's a lot of infrastructure for applying self-supervision to transformer stacks and vision-based transformer stacks. So VITs, I think, are a very clever idea. They let you reuse a lot of the technical software infrastructure that's been built for transformers elsewhere, but applied to images and in a way that also lets you reuse a lot of the self-supervision techniques that have been also developed for transformers elsewhere. So lets you port over a lot of this hard work that the community has done elsewhere and apply it directly to vision and, for the use case we care more about, to scientific systems like PDE systems. Okay, with that, let me just kind of dive into the tutorial itself. So you've probably seen this picture a few times now. You have, the transformer, you have the, encoder, the decoder. In many ways, like the transformer is a complicated object. We'll try to talk a little bit through some of the intuition for what the transformer is doing, but maybe might be useful just to share my general sense for what the transformer is doing that's interesting. One of the core ideas of the transformer is something called self-attention. So in different deep architectures, there's always a challenge of if you have a collection of inputs coming in, how do you learn the potential, correlations and structure amongst the input? If you have something like a fully connected network, what it does is it says, well, I'm just going to, have a matrix multiply of weights going against the input vector. And that matrix multiply, touches everything. So in theory, it should capture all the structure. In practice, that's not fully true. It just is very hard to learn such a big matrix of weights, and it's not usually as effective as you might think. So there's been a lot of work in more recent years looking at things like, say, graph convolutions, where you re-leverage some known structure in the input data. Maybe the inputs form a mathematical graph. And then what you say is that, well, rather than doing an all-to-all, comparison through weights, I'm going to do a, say all to few, where for every node, I look at the few neighbors it has, and I can just coordinate information amongst them, and you set up the weight multiplications to operate that way. This turns out to work quite well if there is a natural graph structure, but in other cases, it's less so. It's not quite as apparent. Like perhaps there's some type of there is some all-to-all interaction. Maybe it falls off gracefully rather than all at once, the way it would in a graph. Maybe there are a few cases where, in some data points you have all-to-all comparisons. Most data points you have only local behavior. So there's limitations to graph convolutions that I think have made them, as of now, not so interesting in, say, a task like computer vision, where there's usually a more structured convolutional network that's pulling information. So I think that, what's really, at least to me, clever about the transformer is that it is a intermediate between, say, the two. Like the self-attention mechanism allows for a type of all-to-all, all-to-all, say, comparison, but it does so in a way that is, more scalable, easier to train than the fully connected network. Um, so, there is a mechanism that is explained often in terms of what are called queries, keys, and values. You think about, say, the input, like I believe the original idea there is like you think about, say, whatever input representation you have as a key value store, and the new data coming in is, effectively querying the key value store in a rough mechanism. Um, and there's an equation for this that's quite nice. You have the Q K transpose, and put a softmax on top of that and then you multiply by B. So query key value. Um, I will have to confess, I've always found these equations quite opaque. There's several folks who try to explain out like how these equations were derived and how they make sense. I think that the practical matter that it does is that it tends to work quite well, and it does satisfy that property of actually enabling that all-to-all comparison in a way that is it provides basically the softmax mechanism here provides a natural mode of soft fall off. So you basically are computing an inner product between, say, whatever query you have, different data points in the input, and then you're turning that into a score, and then use that to reweight the contributions of the relative inputs. So I kind of think about this as mentally like a type of soft graph. In a regular graph, you have hard edges. There's either an edge or there's not. In this type of self-attention mechanism, there's a type of soft graph where the softmax is sort of a partial edge. And this enables you to get, a lot of the benefits of the graph convolution, but also have it be dynamic. It's sort of like a graph whose structure can change, which is, quite cool. Again, I think these equations are really cool. Like, I think it is intuitively, at least for me, the way I think about them is that they are a soft version of a graph convolution. Different folks have different ways of thinking about it. I definitely encourage trying to work through the equations once or twice, but I think it's at times for these types of models, at least I find it very difficult to pull actual knowledge out of the equations. I think you kind of mess around with things until you find something that works. In this case, a transformer works beautifully, so it's really brilliant deduction, but maybe at least one useful analogy is it's a type of soft graph convolution that preserves some of the all-to-all strengths of the fully connected network, but without the difficulties in training it that arise in other contexts. All right. So then how do you apply one of these things in practice, right? So let's say you have some type of input sequence, then you basically embed each word. You run it through this, softmax of what is it, QK transpose and then times V. And then at the very end, you kind of get out outputs. And then there's a few different tricks that you'll see often. So oftentimes you have what are called multiple attention heads. So if you have one notion of attention, maybe you can think the multiple attention concept is actually pretty cool. You say that, well, if rather than having one soft graph structure, maybe we actually have multiple soft graph structures that are learned that highlight different parts of the behavior of the input. So it becomes quite useful in practice to have these multiple attention heads as a mechanism for encapsulating different ways of looking at the input data. And then you can stack the transformers, of course. So you can apply multiple layers of these heads to, again, get an effect similar to a convolutional network. So I think, there's been a few papers recently people have shown like with a lot of hacking, you can get multi-layer perceptrons, you can get convolutional networks to recapitulate a lot of the strengths of the vision transformers. So at least for me, I don't like to think about any one architecture as like, the end all be all of like it solved some problem that other architectures couldn't. I think it's a combination of like sometimes there is a clever idea, but it's also sometimes it's easier to implement, or other people have already implemented code for it and you can leverage it. So the transformer, I think the vision transformer fits into a sweet spot there where, again, there's lots of code out. There's really nice infrastructure for doing self-supervised learning, which we'll talk about later. And it tends to work pretty well. Again, I will say there's more than one view on this. I'm sure some of you in the audience, I can't see you, but are like, no, this explanation is completely off. I definitely think there's room for kind of more interpretations, and in some sense, what matters at the end of the day is the empirical output. when you actually try these things out in practice. So these are more, stories we tell ourselves to help us gain intuition. Um, at least I haven't found a mathematical derivation that quite feels compelling to me yet, but that doesn't mean there isn't one or that you couldn't find one. So with that, maybe let's now, that digression into general transformers done. Let's talk a little bit about just how, what we actually started this particular tutorial on. Like, how do we apply this infrastructure to handle images? So transformers, if you look at the original papers, they're often based on derivations from sequences. You have a sequence of inputs, and then you apply this, softmax attention mechanism, and then you get out a sequence of outputs. So it's another way of looking at it is maybe it's a descendant of something like a seek-to-seek model. But then an image is not naturally a sequence, right? An image is like, a spatial object. And if you're looking at scientific applications here, there's also a spatial object. So there's a natural question of, how do you convert an image into a sequence? And then there's a step here that's critical that I haven't talked too much about yet. That's called tokenization. So whatever input that comes in, you need to kind of convert it into a set of tokens, basically make it into uh, like a more limited sequence space for listing, rather than say passing in raw chunks of an image or raw text into the transformer. You need to change the representation. So how do you then do the tokenization? How do you convert the image into those tokens? And then how do you pass that in? So the vision transform paper, I think this came out, the VIT paper in 2020, came up with, I think, a quite nice way of doing that. It went very simple. What it said is like, well, the full image is quite big. What if we just cut the image up into patches? Um, and then, okay, that gives you some patches. It says, but is that enough to actually reconstruct the image? Well, no, you need some degree of like I guess you could jigsaw puzzle it based off context, but typically you need for an algorithm, you need some more context based on, say, the position of each patch. So it uses something called a position embedding, which embeds, learned representation of the input position uh, of each patch in the image. With the combination of these two factors, it then becomes possible to effectively reconstruct the image. And then you can now treat this entire operation the same way you would treat, say, um, say, transformer sequence-based task. So it's quite a clever idea. It says, let's just reuse this simple patching. But I think, more than the fact that you figured out how to make the wires work, it's just like this actually tends to work fairly well. Um, so to look at maybe a closer example on how you'd actually do this, you can take, say, an image, you can cut it into non-overlapping patches. You can play some tricks here. I think there's different ways you could have like slightly overlapping patches. I think there's room to fiddle with this a bit. But the general notion is, again, you deconstruct an image into patches. Then for each patch, you put out um, you concat it with a learned representation of the position, and then at the end, what you have is a sequence. And in the sequence, you can then feed that into a vanilla transformer. So the nice thing is that you can reuse the usual transformer stack, but you've just done a embedding slash encoding hack to turn the image into a representation that can be fed in to a downstream transformer. So again, this is, I think, a really cool idea. It just makes it easy to re-leverage the transformer. And again, you might say, why bother doing this? Well, one, you might believe the transformer lets you, say, capture global information across the image through self-attention in an interesting way, which I think has been borne out at large-scale studies to some degree. But you might also just say that, maybe you want to reuse some like self-supervision techniques or things like that that transformers make easy. Jumping ahead a little bit, I think one of the core techniques that for self-supervision in a transformer is you do something called mass language modeling. If you have a sequence of, say, inputs coming in, what you do is you mask out some of the inputs, and then you ask the transformer to train on an objective of predicting the masked out objective. So it's sort of for a sentence, you're saying learning how to say predict a missing character or a missing word or something like that. Um, for a image, you're basically doing a missing patch prediction. Now, I'll note people have done missing patch predictions elsewhere. Like this is a idea that's come about in multiple contexts, working with convolutional networks or other architectures. So patch-based infill pre-training is definitely not a new idea that the transformer community came up with. But I think the nice thing is that you can re-leverage basically a full NLP-based stack from mass language modeling. And because you've done this in input encoding, which I think is quite nice. So you might ask, what is that position embedding learning? And one way to think about it, and this is a kind of a similarity matrix, it's learning something similar to a soft representation of the position directly in the input of the patch. So here you can see for all the different patches, you have like the patch row and patch column. What you find is that like it is roughly something like a soft encoding of directly of the patch position, but in a say a little bit friendlier format. If you sometimes, like, again, this is a trick that arises often in deep networks. If you have some type of like hard number you need to encode, sometimes networks just don't pick it up. So oftentimes there's a notion of like a fuzzy soft embedding. You take, and again, I've seen this in like, for example, in some machine learning for quantum mechanics, like you'd have, say, some like hard numbers and you'd find a way to like expand it out into a softer vector. So I think of the position embeddings as kind of like that. Like, let's say if you just have a vanilla sequence, you might say, well, this is in position 4, but the network's going to find it really hard. Like 4 is one number. So instead of you like, split out a vector, you could maybe one hot encode it, or you could even have a soft encoding that peaks at 4. And I think networks just empirically seem to find this a lot easier to deal with and learn much better. I have to confess, I don't have a deep theoretical explanation for why precisely. If I had to wager, it's something about, the operations are all, they're kind of extensive operations. Like the more dimensions you have, I think sometimes it matters a bit more to the architecture. So expanding it up, blowing it up to higher dimensions sometimes makes it pay more attention than if it were just a single number. But again, I don't have a proof for that. It's quite hard to prove anything about these models. But that's not to say it is impossible to work out a nice theoretical explanation, but empirically, this seems to work quite nicely. All right.
But
So,
Bharat, a couple questions on that front. In that position embedding, is there some robustness to um, symmetries that the image might have? Like if I gave a rotated image, right, is there a sort of a natural way in which those position embeddings, uh, is there a way sort of in which you could take a unrotated image, right, and then apply the rotation operation, right, and then be able to get to the position embeddings sort of in a clean way, or is that sort of not something that these embeddings respect?
that is a really good question. I've not thought about it. So like the transformer itself is one of the weaknesses really is it's position well, weaknesses or strengths depending on how you look at it. It's order invariant just by the structure of how it's done because you're kind of adding things typically somewhere. So you don't tend to respect, say, like the relative order of the inputs, hence the position encoding. Now, how does the position embedding deal with rotation? I have to confess, I've not thought about that. I haven't seen something in the literature either. Um,
Yeah, because if you look at, for example, what Payal did in the Molformer work, right? They brought in this I guess periodicity, right? Like, it doesn't matter whether you read from the left or the right. Um, and so I wonder if there is a way in which, of course, in higher dimensions, right? There's probably another way in which you can sort of um, represent that directionality. Um, right? It doesn't matter if you read it from bottom onward or sort of top right, right? So in 2D and then similarly in 3 dimensions. So I wonder if there's some other ways in which we could do that. I'm not sure if
hmm.
Anushka or Alex have any thoughts here.
I think there's a concept of relative emojis and rotary embedding for vision, similar to what they use in Montreal.
Yeah, I don't know if you did this. Has anyone tried rotary embeddings?
There people tried rotary with vision.
Or rotary embedding. Anyone has done it? Should try.
Another one that I've seen where they do keep out. There's another one I've seen where they do key values. So it's another, you like Warner function to come up with your embeddings. Haven't really poked that much further on it.
All right, great. Thanks. Yeah, Bharath, keep going.
Yep. No, really great question, I think, Venkat. And one thing I'll just mention is like, I think even for like the rotational embeddings, like there's definitely some, not controversy, but I think questions about like, what is the right notion of embedding? Like my rough sense was that most embeddings were roughly like inter-exchangeable. Like, I don't think like, there's some folks like the rotary embeddings, some folks like, more standard position embeddings. Yeah, I don't know. Like, I'll have to think about that one. Really great question. Thank you, Venkat. Okay. So maybe, jumping now back to actually maybe a nice segue into thinking about applications and different scientific foundation models. Like there's been a variety of different papers that have come out in the last, I think, couple of years, starting to look at applying transformers to in PDE systems in particular. So to roughly summarize like the idea here, and you can see this quite beautifully from many of these images, you have when you're solving a PDE, you're effectively creating, maybe it's fluid flow, maybe it's some other type of like flow on a system. And you can more or less view these flows as images, which traditionally is the way people, think about and study the flow. But you can then take those images effectively and feed them into a transformer stack or architecture. And again, you have all the nice benefits, like there's a lot of work done on transformers already for pre-training. You can reuse nice libraries like Hugging Face. So again, this has spurred a whole bunch of work here in terms of thinking about how do you actually, study a PDE with these transformers. And you might step back and ask, like, what's the goal? So there's been some, traditionally, of course, when you're solving a PDE, you use, some numerical, finite element method or something like that. And then you solve each PDE basically one at a time. So from there, you've kind of gone to the idea of like, so, and then there, say you have, say, some input condition, you then, solve the equations, you get the output condition. So after that, I think there's really nice, work, by Anand Kumar and other groups where they're looking at, say, like learned, neural operators. So the idea is that there you learn an operator that means for given any input, you can say time evolve or do whatever the PDE is doing, go directly to the output. And this is really cool because in many cases, it allows you to rapidly approximately solve a PDE, at least within a domain of coverage. And this is, for some fixed set of parameters for the PDE. This has been really cool. I think it enables a lot of like cool new applications. It spurred a lot of thinking, but there's still a limitation there, which is that you're learning roughly, say, one equation and not just one PDE. You're learning one PDE with one given choice of, say, parameters, hyperparameters on the PDE. And this means that it tends to be fairly, you have to basically learn one operator and then keep it around. It's not quite general to different systems of operators. And the reason I think intuitively that we expect there should be some generalizability is that, by eye, you can often, gauge how, if things are going well. So if you see like a Pixar movie and you see the water flow, you'll notice like the water often flows beautifully. Like it looks like it's real water. Whereas if you see bad CGI, the eye will immediately pick up saying, oh no, they messed up CGI, the water looks jank or something like that. So intuitively, our brains are already capable of like for a broad range of systems. And you think about bad animation in general, when things look right, when things don't look right. So intuitively, our brains have a rough mental, PDE forward solver already. So we know it's possible. So the question is, can we, take something that is like this neural operator concept, but rather than just solving one PDE, maybe, find a way to transfer information across multiple PDEs. And, the dream would be ChatGPT style or something like that. You learn some, deep fact about PDEs or time evolution in general. So again, this is a very, I think, bleeding edge field. I think a lot of these papers are out maybe in the last year. So I won't go into too many details about each of the papers, but I'll just say a couple of the things that people have been trying. There's a lot of questions around what's an objective function. I believe some of these papers are looking at, say, reconstruction as an objective. You put in, say, the input, you patch it, you tokenize it, you add these embeddings, then you're doing a reconstruction on the input that came in. There's some neat ideas in particular about saying, like the full self-attention doesn't necessarily need to make sense. What if you did it axially? What that means is like, if you have a three-dimensional PD, you have height, width, well, I guess in this case, two-dimensional height, width, and time. You can then have a more limited form of attention that is only comparing things along an axis at a time. And I think there's some physical justification for why you might want to do this that is interesting, but it's also just a lot cheaper. As even though the transformers are quite nice to implement on a GPU, there still come limits when you have big images with lots of patches. So some of these hacks and tricks can be quite useful. I think there's also neat notion that's arising about like in general you don't study PD, like each PD is kind of studied and it's by itself, with some information brought over from other techniques elsewhere. But you think about Navier-Stokes or whatever equation you're looking at, like more or less as its own entity. But what if you can combine information from different PDE systems? Again, like there's some neat concepts here that I think it's not fully proven that this works well in practice, but I think it's spurred, say, a lot of the work that is kind of coming out here. Other things like, there's a lot of details in some of these latest architectures. Maybe as a quick note, of course, the usual trend is whenever you have a new field, you get these really complicated architectures that have a lot of bells and whistles. Then it takes some time for things to simplify down and figure out what's going on. So we have some references here for you to check out. Definitely encourage you to go read them yourselves. There's some neat ideas. There's these Swin blocks that I think, I believe they said state of the art. They're like one of the first.
Yeah, and Max presented yesterday on this. Yeah.
Okay, sorry, I didn't know. Okay, you already know what that is, so I'm not going to say more about it. But I encourage you to go out, check the architectures directly. And again, there's a range of different, I think someone presented on Aurora, I believe. I think you've seen different contexts of these. The rough sense I'd say is like it's useful, especially now that for all of you, you've seen several of these different architectures. Like I would think it non-controversial to say there's still a lot of, general confusion amongst researchers about what is the quote unquote right architecture. So you might just want to look, what are the ideas that are actually, make sense here and that can be carried to new contexts. Again, so I think there's a new field, like a lot of these papers are basically out in the last year. So lots of questions over, what is the objective? What's the tokenization? I'll just briefly mention, we put out a paper, I think, on arXiv just a few days ago. Actually, Amal and Brun, who's not here, were the lead authors on this. And here we looked at, say, like a variant of this where we looked at, say, for a given PDE system, how well can you measure generalization across the parameter space? So if you learn, say, on for some values of parameters, can you actually generalize well to parameters that are further outside the space that you've studied? And can you combine information from different choice of parameters when doing this pre-training? And what I'll say is like it's an early set of results. Things are still in progress. When you look at, say, in domain, which I believe are parameters that you've seen or nearby to parameters you've seen, things tend to do quite well. But when you start looking at parameters further outside the space that you studied, generalization becomes hard. So again, there's a lot of like different techniques that are rising. I think, looking at the plot on the right, I think one lesson is scale matters, as is always the case with transformers. There's some degree of generalization that these things are picking up where you're able to pull information from different parameter sets. But I'll say we may well just need to go to much larger scale. Like if you look again, the GPTs, et cetera, there's always a like scaling law or something that kicks in on these systems. So there's a lot of work to be done, figuring out, what is the scaling law for these PDE systems? What scale do we expect? Is there a way to, a big part of this is like we use, I think, PDE bench to get some of this training data. Is there a way to, which it took a lot of effort from the authors there to put up that many simulations? Is there a way to get more training data cheaply without having to run expensive simulations? So I think lots of cool ideas and work in the field. And hopefully, I'll just punt over to Amal in a minute to present some of the code. Once you're able to actually work with some of these notebooks and code, you might be able to try some of these ideas out for yourselves. I think with that might be, yep, I think we're just about done there. So if there's any questions, I'm happy to take a crack at answering them at least. Or if not, we'll pass the torch over to Amal to present in the code section.
Yeah, great. Maybe we can run through the code and then take other questions at the end.
Yeah, so this notebook is up on the repository for the summer school, so you could like follow along. It's basically a very straightforward walkthrough of how you would go about implementing your own vision transformer using PyTorch. Yeah, so initially we'll just start off importing a bunch of libraries, in particular PyTorch, and we'll use PyTorch Lightning as well. We'll sort of run a very trivial image classification task on the CIFAR10 dataset. We'll essentially follow what the original vision transformer paper did. Yeah, so because we don't want to train things now, I'm just going to load a pre-trained checkpoint that's already stored somewhere on the internet. So that will make life a little bit easier. Okay, so obviously the first thing that you want to do is augment your data a bit, add in a few transforms so that your model doesn't overfit. Then you want to generate your data sets, test your trained data set, validation data set, test data set, create the data loaders for those, typical of what you would do in PyTorch. And then let's quickly visualize what's in the data set. So the CIFAR10 data set is basically a 32 cross 32, a set of 32 cross 32 images, which have 10 distinct classes. 5 of them are animals, and I guess 5 of them are vehicles. And the end goal is to accurately classify these. Yeah, so like how Bharath described, what we do in a vision transformer is essentially take an image, patch it up, do a linear projection on those flattened patches, add a set of learned embeddings, and then pass them to our transformer, and then we take out the final token, and then pass that through an MLP, and then do our classification task. Okay,
Great.
so
Well, sorry. Should we maybe just pause here for a second and ask if there's any questions so far? We've already covered a good amount of material. In terms of anything in particular, it's worth for a minute just like pausing. Like this animation does a really nice job of actually showing the idea of what's happening in the vision transformer. All right. Looks like everyone might have perfectly understood. So, okay, go ahead, Amal.
yeah, so we'll go about how to implement each of these parts so that we can get to this end product essentially. So the obvious first step that you want to do is being able to break up your image into patches, and that's relatively straightforward. You essentially just need to reshape your image and break it up into patches of whatever patch size you want, and then flattening depending on what you want to do with your model. You can just flatten the image outright across channels or not across channels. So we'll just quickly visualize how this patching up is. You can see it's a very low res image, which is not unexpected because we're breaking up into patches of 4 cross 4. Yeah, but essentially very straightforward way of breaking up into patches.
There's a question on how do you think about selecting the size of the patches?
Yeah, I think that's just a hyperparameter that you do. That's typically how people go about it. And I guess depending on maybe more specifically for like PDs or something, what scale of features you want to capture. Sort of also becomes a question there.
This actually, I think, it reminds me of the discussion we had yesterday, right? About what are the sort of what are the right ways to tokenize, right? And Alex Brace was talking about k-mers, and not if you just have sort of single alphabet, right? ATCG, right? That doesn't give you sort of the full thing. And then I think today Gautam was talking about codons, right? And so I think there's a similar sort of analogy between sort of information, the building block, right, has to have information that is unique, right? So the reason to sort of have the three-mer, right, is there are some unique three-mer blocks, right, that sort of capture inherent sort of hydrogen bonding and other things between those, right? So such that those then become good bases from which you sort of build up your sequence. So I wonder if there's some information theory style thinking that you can bring in, right, in terms of how to pick this batch size?
Yeah, I guess it would largely depend on your data set as well, especially for scientific tasks. This makes a lot more sense. I think like for a traditional image classification, probably not as much. It's probably just a hyperparameter that you can pass through. Would be my guess.
Guessing the answer is no here, but so like BPE is like originally compression algorithm, right? Used to shrink down like the number of tokens and texts. Has there been like anything of applying like traditional image compression? Because it looks like right now you know you're taking that patch and then it becomes just a straight linear vector. Whereas like the simplest thing I could think of would be like JPEG, where you're basically just doing a Fourier transform and then truncating your higher mode or higher frequencies.
Yeah, I'm not aware if there's work. I probably wouldn't be surprised if there is.
Okay.
I mean, I'm not aware of any. Sure, but I wouldn't be.
Got it.
Yeah, I wouldn't be surprised if there is. Yeah, but I'm not aware of such work. I probably wouldn't be surprised. I guess people have tried a bunch of different stuff. So it might be.
Is it typical that the embedding size of the token is larger than the patch size?
Yeah, that's almost always the case that I guess that just comes out explicitly. Would be my guess.
Okay. Cool. Thank you.
Yeah. Okay. So now that we've broken this into patches, the next thing we want to build is our attention block, which is the main key thing in all. So essentially, the attention block is just a layer now, and then your multi-headed attention. Fortunately, we don't have to implement our own self-attention block. It's provided by PyTorch, so you can just go ahead and use that. And then we just have layer norms and before it goes to the attention block and after, before it goes to self-attention and after, and then at the end, we have a neural network.
So also, we'll just quickly jump in. I think it's a one resource, and we'll send this over to you. There's a beautiful paper from DeepMind. It's like Amal, you know what I'm talking about, the pseudocode for transformers paper. Like if we could maybe share that with folks, like it's worth as an exercise. I recommend trying to code your own like multi-head attention or attention node. And again, this DeepMind paper has some very beautiful pseudocode for like all these algorithms. So it's worth just taking a minute to like as a learning exercise, try implementing your own version of this. So if you need like, again, PyTorch has everything. If you're just trying to get to results, you can absolutely use it. But if you want to actually try implementing, very nice exercise. And Amal, you know the paper I'm talking about, right? Sorry, I know you're drinking some water there, but the pseudocode, we should, if it's not been shared already, we should make sure to share that in the slides later.
Yeah, we'll add it to the tutorial.
Okay, sorry, didn't mean to interrupt them all. Please go ahead.
Yeah, no. Yeah, so now that we've built the attention block, we pretty much have most of the key features that we need. Now all that we need to do is add in a learned position embedding and an MLP head at the end, and then just project these patches. Yeah, so we'll essentially build up the entire module that we need to train. Okay, just maybe. Yeah, I'll just keep it here. So, yeah, initially what we want to do is break this up into patches. We've already implemented the function for that. And then what we want to do is generate these class tokens. That is this specific for this task, which is essentially just a bunch of parameters that you want to learn. And then we concatenate those patches along with these. We concatenate the class tokens with your patches. And then we add in a position embedding to these tokens, which is essentially another just set of parameters that are learnable. And then we pass this through what we call the transformer over here, which is essentially a sequence of these attention blocks that we defined earlier. Yeah, and because it's a classification task at the end, after passing it through a bunch of these attention blocks, we just take out the token and then pass it through an MLP, and then that's our output. And yeah, we'll use PyTorch Lightning to just set up the training. So we, again, this output of this model, we define the laws to be a cross entropy laws, which makes sense for classification tasks. And we just set up our optimizer and scheduler and everything, and then just carry out the training. Yeah. Yeah. So
Sorry.
that's pretty much it of how you'd go about setting up a basic VIT.
Quickly jump in there, Amal. Could you just go back to the objective again in this case?
Sorry, go back to the.
Yes, this is a do we have a pre-trained objective example here?
Do I have a pre-trained?
Yes.
Yeah, I mean, I have results on the test data set. So essentially these are the hyperparameters that are tuned for the specific model. They've run a tuner and ended up with these for the best set of results. And so I mean, just because it's a classification task, there's no really output except for the accuracy of the model. And this VIT ends up having about 77% accuracy on this data set, which is actually not that great. But it's also not very surprising considering that the data set is quite small. On something like ImageNet, which is a much larger data set, this performs significantly better. But yeah, nevertheless, the goal is just to show how to construct your own a simple basic one. And I think.
Sorry, Amal. Just to quickly clarify the question there, like, do we just are we doing direct supervised learning here, or is there a self-supervised objective as well in this particular example?
No, it's just
Direct supervised. So maybe might be useful, like maybe we could pull up the repo from just like our paper, like and just quickly show what that looks like, and we can incorporate it into the tutorial for everyone to try later. Like, do you have the? I know our repo code is a little bit messier, but is there an example there we could pull out and just maybe quickly show what the self-supervision objective looks like?
Yeah, maybe while you pull that, right, I think we can take a couple questions and then you can pull something from there. Okay, so I think that Bharath, maybe you can take this question on integrating image and text together. So I think this goes to this whole notion of multimodality, right? So yeah, maybe you can talk about how to merge the tokenizations there.
I think that's a really good question. So I know there's different strategies people put out. Like, I think the simplest one is just you have two different tokenization schemes and you like glue them together, which I don't think works terribly. Some folks do try to like, there is usually an embedding layer trying to merges the different modalities into like the same embedding space at some point. I think the tokenization schemes offhand are kept different, but again, I'd have to check the details. Like, the devil's in the details in many of these things. But I would like to say in this case, for basic multimodality, you can probably get away with just so long as you don't have overlapping tokens or there's direct collision or something that's happening, you're probably fine. And it could be useful because like yeah, I think like there's also like even for this came up earlier for like the size of the patches, but even for like regular transformers, there's always a question of what's the size of, say, like, are you doing a byte pair encoding, or are you doing a character level tokenization? There's questions there that come up about like the size of the tokenization that arise there. So there's several parameters you can tweak. But my guess is if you have enough data and you take a reasonable choice, then you just make sure there's not a direct collision in the tokenization schemes, you probably get a basic multimodal architecture that works fine. I'm not sure if that answers the question, though.
Yeah, I think so. I think that's good.
Yeah, I maybe show just a quick example of something that we've done.
Yep, got them all.
For the self-supervised task. So essentially the logic is pretty much the same. But the way we go about doing patching is slightly different. We don't just flatten it and I guess pass it through an MLP. Instead of what we do is use a convolution where the stride is essentially the same as your patch size. So you have convolutions essentially the convolution is doing the patching. Essentially, I guess end product is the same. It doesn't really change, but it's just another way of going about it. And then the same as usual, you add in your position embeddings, pass it through your VIT. And at the end here, because what we want to do is sort of reconstruct some kind of field that's similar to what the input we passed in is, we do essentially a transpose of a convolution to essentially recover something that's of a similar dimension of what we passed in. And yeah, and now the end goal is essentially this specific task is to transform an image at particular time step to the next time step. So because of this transpose convolution, we essentially get back something that is similar to what the input is, but ideally at the next time step. And the goal now is to reduce the error of the prediction. This would be a self-supervised way of going.
Do you have the code Amal just to show the actual objective function we used? That might be, again, a useful little bit of reference for folks. This also provides the objective, that is.
I haven't looked at this in a while.
Sorry, I know we're putting you on the spot, and
Yeah,
there
it might take a
apologize
bit.
about that. But okay, hopefully that gives you everyone like a sense though of like how you actually can apply one of these things in practice. Like conceptually, it's quite simple, right? You just find a way, like as Amal showed, you cut up your image, whatever that is, into patches. You feed it into one of these things. You stick some reasonable self-supervised objective. There are some choices there. Like some folks like the full reconstruction. I think we did something closer to mass language modeling in our particular variant of it. You might try experimenting with different versions of this. And of course, I think the hard part is you need to find a high quality data source. If you're doing like PD modeling, again, you're probably looking at like reference simulations that have come out from elsewhere. Or you can run your own simulations if you have access to adequate computing facilities. But conceptually, the idea is quite straightforward, and you should be able to use the code in the tutorial notebook relatively straightforwardly on maybe PD systems that you're thinking about. And I think, later we'll go in and add in maybe a simple example adapted from our paper on like 2D tutorials, so you can get some idea of how you apply this on a physical problem. But I think, I'm not sure if we might be coming up closer to the end of the session. Are there any more, conceptual questions about how these things work, or if there's anything from the code, we can try to dig it out and give you an example of that live, or if not, we'll punt and put that in the tutorial code later on GitHub.
Yeah, I think it was good. It was good to sort of walk through a clear example. And Amal, if you can add a few of these things that we talked about here, and as you sort of saw through the summer school, right? These same ideas have appeared recurrently, and I think Aurora and Climax and Posilion. So a number of these architectures all share these sort of same ideas, and I think as Bharath mentioned, right? I think we're not quite at the point where these have all unified. So so it's a very exciting time, and I think the PD hackathon team will take this further. Okay, with that, we'll end the morning session, and then in the afternoon session, we'll have diffusion models, which I think will be presented by James Duval, and then we'll have a discussion on neural scaling laws after that. So see you all in an hour and a bit. So see you at 1:30 p.m. Eastern. Thanks.